Okay, so thank you, Sinan. And as he said, we're going to be looking at the late Holocene rupture history of the south central San Andreas Fault at the Van Matre Ranch in the Carrizo Plain, California. So before I start, I would like to thank my field assistants because I couldn't have gotten the work done without them. Rad's here, also Jeremy and Clay, who you guys might know, as well as, and this is also a lovely picture, isn't it? I also like to thank my advisor, Sinan, who took a selfie where all of the other people in the picture are completely invisible. So thank you guys. But let's get started. I broke my talk up into a few sections. First, I'm going to be going over kind of the context and the data and the field area, basically the question that we're trying to tackle by opening a paleoseismic site at Van Matre Ranch. I'm going to go over the methods we use to collect our data. Then I'm going to get into the data itself, including the trench structure, individual earthquake evidences. Then we're going to go over dating those earthquakes, and then have a discussion using data from other sites and kind of trying to put the whole picture together. And then I'll give you a nice conclusion slide. So let's get started with part one, studying the San Andreas Fault, data from previous sites. So overall, we're talking about the San Andreas Fault, which I don't think I need to explain too much to a group of geologists in Southern California. This is the entire length and breadth of the San Andreas Fault, but the south central San Andreas Fault is defined by the rupture length of the 1857 Fort Tejon earthquake, which went from down here near San Bernardino, 300 kilometers up to towards the Paso Robles area in Northern California. This part of the fault, which I will hereafter refer to sometimes as the south central San Andreas Fault, sometimes just the San Andreas Fault. But know that we're talking about this part of it. It's broken up into several blocks. You've got a Mojave blocks, Big Bend blocks, Carrizo blocks, and Shalom. And this is what part of the San Andreas Fault we're looking at specifically. So a little bit about the San Andreas Fault. Obviously, it's a pretty big potential hazard as far as earthquakes go. The Fort Tejon earthquake that defines the length of this part of the fault was 7.8, occurring in 1857. And you've got a slip rate of 34 plus or minus 3 millimeters per year for the past 3,700 years. So this is an assumed constant slip rate. So the questions that we're trying to answer by opening this and other paleoseismic sites along the fault is, what is the long-term rupture behavior of the San Andreas Fault? And what is the timing and magnitude of the past earthquakes that have ruptured? Essentially what we're looking at is, how is it that 34 millimeters per year is accommodated by actual slip during earthquakes? For example, you can't have 5 Fort Tejon style earthquakes over the course of 100 years. You're not generating enough slip from that 34 millimeters per year. So we do have a constraint on how much slip can be occurring. And so going on that assumption, here's a little couple models that we use to think about it. Now this is a pretty busy figure. I want us to ignore this top section for now and just look here at the bottom. And what we're seeing is this y-axis is showing us cumulative slip. So that's representing that 34 millimeters per year, always accumulating slip. And each of these are representing individual earthquakes that are accommodating that built up slip. There's a couple different ways that it could be occurring. One is the uniform slip, where you're having, for individual sections, earthquakes of the same slip. So in the Carrizo, for example, in this particular adaptation, you have large earthquakes accommodating that slip, but they're less often as the smaller earthquakes. But in each of these regions, the slip is uniform. You're getting the same amount of displacement. There's also the variable slip model, which says that you're going to get all sorts of different kinds of slip to accommodate that 34 millimeters per year. So going back to what we're looking at, so if we're dealing with the timing and the magnitude of these earthquakes to better understand how that slip is accommodated, there's a couple of ways to look at it. One of the ways that we can get actual magnitude of earthquakes as a proxy is using rupture length. We can also use that rupture length to approximate what kind of slip you might get on the ground. So these are a couple of things that we're going to be looking at as we go forward. Constructing the actual record itself, I'm going to go over a little bit just because we're going to see this particular type of figure quite a lot in this paper. So I'd like us to understand what we're looking at. So here's the length of the San Andreas Fault, the south central San Andreas Fault, as well as individual paleoseismic sites that have been studied in the past. This red line is represented on the x-axis of this plot by a 0 to 300 kilometer length line, with this being the south near Wrightwood, Pallet Creek, and Little Rock, down here, going north through Fraser Mountain, Van Matre Ranch, which is where our site is, Bedart Fan, and north to Annette, which is a paleoseismic site that's currently being worked on by Alana Williams at ASU. So as an example, how an earthquake will look along this is 1857. We have our y-axis representing the time portion of this figure. 1857, we have it well constrained. It ruptured the whole length of the fault. So it looks like this. 1812 is a rupture that is historical, but is not well constrained. So it's represented where we know it ruptured and then has a question mark after it. So using this, we can actually build a record and kind of visually represent these earthquakes through time. Here we have Fraser Mountain, which was right in the middle in that Big Bend block of the San Andreas Fault. We have a number of earthquakes. I'd like to note while we're looking at it that there are 7 earthquakes here. There is a 6th that they have evidence for, but it was poorly constrained. So each of these earthquakes has a corresponding time period in which it could have occurred and a probability density function showing the more and less likely portions of that timing. And these will connect just like this, pretty straightforwardly, right to your faults. So earthquake evidence collected at a single site can now represent a series of faults. And when put all together, we have an overall picture of what it is that we're looking at with the San Andreas Fault. You have a number of ruptures, 1857 going across, Bedart Fan having 5 ruptures noted other than 1857, Fraser Mountain having 7. Again, this one is poorly constrained, but this is actually a dashed line right through here. It's an assumed full-length rupture. But this is kind of the building blocks of how we are looking at this data. We can look at this plot and see that there are a decent number of uncertainties. A lot of these faults are extended, or these ruptures are extended past where we know or understand they might go. These are individual sites with individual records, and we're trying to put that data together to get an idea of what the rupture history is. So now we're going to talk about how we collected that data at Van Matre Ranch. So the first question to answer is why VMR? There's a couple of reasons for VMR, but one of the big ones is that we're trying to fill this gap in data that exists between Fraser Mountain and Bedart Fan. It's a pretty wide area. As you can see, there's a lot higher density of paleoseismic sites in the south, much less so as we go further north. So Van Matre Ranch is an attempt to fill that gap. One of the benefits of having Van Matre Ranch be so close, it's about 20 kilometers south of Bedart Fan, 80 kilometers north of Fraser Mountain. One of the benefits is that we were assuming essentially that ideally the Van Matre Ranch site would have an identical record to Bedart Fan. They're very close. It's a very concentrated part of the San Andreas Fault. And one of the things we're hoping to do is not only to duplicate the data that we're getting out of Bedart Fan, but also put tighter constraints on those earthquake ages. So to do that, we look at the overview of the Carrizo Plain, which is right through here in the San Andreas Fault, highly concentrated. The actual orientation of the fault through this area is almost exactly what the orientation is of the Pacific Plate moving. So you have a highly concentrated fault that's running through the entire area. It's very easy to locate on the ground because you have a number of displaced features, so you can get a good idea of where the fault is. There's been a number of studies already done that show that you can get that you can get a good record of the last 1,000 years depositionally, which will allow you to look at the history of the site, and that there are datable materials coming from the Temblor Ranges, which are the hills to the east. So we opened up our site. Here's a nice view. This is the boundary between Van Matre Ranch and BLM land. We went as far south as you could possibly go without having to be on BLM land. Here's a nice LiDAR image where you can see that there's a very visual component to seeing the fault trace on the ground, so it's easy to identify. And here's where we excavated our trenches with the strand of the fault going through. We have trench 3, trench 4, and a fault perpendicular trench connecting the two. Here's some fun pictures of us actually excavating the trench, mapping out where we're going to dig with the backhoe, putting in shores, and then having Sinan clean the entire trench by himself.
Nope.
Which we thought was funny. See, I put a video in it, Sanan. I told you I would. So we have our trench now, and we're going to actually look at what we were looking for in the trench. And paleoseismology is the study of geological indicators of past earthquakes or ancient earthquakes. So what we're looking for is stratigraphic evidence of faults. Some of that can come in the form of vertical displacements, facies changes, and thickness changes. These are usually, these can be accomplished by strike-slip faults very easily by displacing different parts of the fan against each other. Usually something like a facies change would indicate more displacement than would something like maybe a vertical offset. But kind of the best evidence that we can find, and one of my favorites, is when we find a fissure. Because a fissure will indicate not only that an earthquake has occurred, but will give you a very clear idea of what was at the surface during the earthquake, and then what was deposited just after. Because you create the fissure with the surface rupturing earthquake, and then that fill is with the first unit to deposit on top. So if you can date the unit just below and the unit that actually fills the fissure, you can get a really good constraint on when that earthquake occurred. So in order to get this data, we create trench logs. These are not my logs, but we create high detailed 1 to 10 scale trench logs of all of the important walls. We create a photo mosaic by taking hundreds of pictures of the trench wall and modeling them together in Agisoft. We make printouts so we can actually map directly on the images of the trench wall. We distinguish stratigraphic units, lithological packages, earthquake evidences, and we also collect detrital charcoal samples and label where we collected them from, which is a very important part when you're talking about dating earthquakes. So this is what my digitized logs look like from a zoomed out perspective. There's a lot of detail missing in these, but this is kind of a simplified version of my trench log. You see here that trench 3 and trench 4 are actually a different size, which is reflected here. And that's because we had a partial trench collapse right around here. So we could only excavate to a certain distance. Another thing to note is that we have this featureless fault zone, and that's actually where you have the trace of the San Andreas fault running through. So all of our important data is going to be coming from the western portion of the fault. The eastern portion had a good record of the last 1,000 years, but there were no earthquake evidences in it. And so we're not going to be taking a look at that going forward. After we've collected our samples, we label them. We put them in these little vials. They're mapped out on our trench logs, and then we bring them to Kirby's wet lab, where we do all of our sorting and cleaning so that they're ready to take over to UCI for dating. We also used OSL samples. The UCLA OSL lab came out and helped us collect the samples, and then I was able to go to UCLA and help them prep the samples for dating. So we're going to talk a little bit about how it is that we're actually dating earthquakes and the importance of numbers when you're talking about detrital charcoals. So you have these two cases. We're assuming this is the same trench, same events. One case where you get very poor amounts of datable materials, and one where you get good ones. And you can see the difference in terms of what the ages of these events are constrained to based on what you have. For example, this 750-year-old charcoal, in a trench where you have nothing to support that particular charcoal, you can only say that event 2 occurred before 750. But if we assume that these are the same events, then we actually see that this was almost certainly a detrital charcoal. So numbers are important when it comes to detrital charcoals. The more you have, the more likely you are to be able to phase out those much older charcoals that made their way in. And it's another reason that we used OSL dating as well, because unlike detrital charcoals, OSL is giving you the date of burial, which is more of an in situ age. And you can use that to confirm or deny some of your detrital charcoal samples. Don't worry too much about reading all these. I'm not going to go into them, but we did have 20 plus samples that we were using in our Oxcal model. So we had a number of samples to work with. And now we can actually get into the trench structure and earthquake evidence. So now we're looking at the data we were actually able to pull from Van Matre Ranch. Here's the trenches. As I said before, we had this featureless fault zone, so we weren't able to make any correlations between the eastern sediments and the western. So we're just going to cut that off and start to look at this trench in more detail, the western portion. One thing to note is we excavated our trench along a slight a slight rise, maybe half a meter little slope, which would be on this western end. You don't see it as well because I straightened it out so I could maximize horizontal distance, but there is a slight elevation there. And you can kind of see that reflected in the sedimentary packages we have here where they're thinning as they go west, presumably because they are thinning onto that slight uprise. We have 4 distinct packages. I'm going to talk about the unit labels we give them and the reasoning behind that in the next slide. But one thing to note is that the reason that these are broken into packages is each of these particular colors is separated by these featureless zones of sometimes massive sand, sometimes silty sand. Sometimes we have the one in between our yellow package and our green package, which is actually this boulder-bearing high-velocity deposit of some kind where you have boulders this big in it, which was shocking. But yeah, so that's the overall structure of the trench. Let's talk a little bit about the units because we're going to be seeing them with earthquake evidences. The unit labels are pretty straightforward. We labeled a unit 0 to 99 for all those units above our first earthquake evidence, which would be 1857. We labeled them 100 to 199 for all those units affected by 1857 or the first earthquake. 200 to 299 for those affected by the penultimate second earthquake. 300 to 399 affected by the third, so on and so forth. So that's where the unit labels come from. As I said before, we have these bioturbated or featureless kind of zones of sand or silty sand or class-bearing sands that are in between our packages. These represent unconformities or where you lose some time. So the only 2 earthquakes that we have in sequence are 1857 and the penultimate. After that, they are out of sequence, assumed to be. And we'll see that they most definitely are. For example, this 400s package has this calcium carbonate cement, which would have taken a long period of time to accrue. And we found with dating that the packages here are much, much, much older, several thousand years older than the other packages. This is partially explained by the fact that we have this slight elevation that we excavated along. And this could possibly represent much older sediment that's been moved a much greater distance along the fault and creating that slight shutter ridge along that portion of the fault. Okay. Going forward, we're now going to talk about actual event evidences. On the left here, again, don't worry too much about reading it. It's a lot of words. But I just wanted to show an example of an earthquake log. So we have several evidences for each of our events. So we have 5 events, A, B, C, and D, A, B, C, D, and E. And each of these have several evidences. All of these are explained in detail in our trench log. But going forward, I'm just going to list how many evidences there are. For example, we have 9 for our first earthquake, 1857. But I'm going to go over the highlights. Basically, we have a fissure where we have fill from the overlying unit 50 into a truncated unit 101. That's a pretty clear evidence of surface rupture. For our penultimate event, one of our best evidences is this truncated piece of 200. This is only visible in trench 4, which is why there are only 3 evidences for this particular event. But you get some class breakup and fall in, and you get upward termination into unit 150, which then overlies unit 200, which is a clear distinction that you have an event occurring before the deposition of 150. Event C, this is where we start to get into those earthquakes that are assumed because you have a lot of earthquake-related deformity and displacement, but you don't have that overlying unit. Again, it's a featureless sand above it. But we have 10 evidences for this, including things like vertical offsets, clasts fallen, facies changes, the truncation and disappearance of some units, indicating you're displacing different parts of the sedimentary sequence against each other. Event D, which has very similar evidences, although interestingly, this one has a fissure with fill from this overlying sediment, which is a pretty good evidence, despite how old it is. And there are 13 evidences for that. And for event E, we have 8 across the 2 trenches, and a very clear fissure with 481 filling in this portion of the fissured unit 500. So those are our events A, B, C, D, and E. And now we talk about the interesting, well, we start to get into the more interesting part, which is we're actually dating these earthquakes. There's a lot going on here, but what we use to date the earthquakes is a statistical program called OxCal, statistical modeling program. But basically, OxCal can do a few things for us. One thing it does is models radiocarbon samples, our detrital charcoals. When you get your detrital charcoal samples back from the lab, it's given in years BP. OxCal can do, for individual samples, a conversion from that into calendar years. It will give you curves based on the more or less likely dates for that particular sample, and it gives it in calendar years. So the program also, when given a bunch of samples, can put it into, well, you give it the stratigraphic order. So we found these samples here, you give it a relative stratigraphic order, you put in where your individual earthquakes were seen, and it can give you not only a good idea of the ages of these units, but also ages for your earthquakes with corresponding probability density curves. So instead of looking at all this busyness, though, let's just look at numbers because they're a bit easier to deal with. And so for our ages, using our samples, we have our 5 earthquakes. 1857 obviously is a given. Our penultimate earthquake can be constrained to 1681 to 1796. Remember, again, we have now a period where we're probably losing time and we're out of sequence. Event C between 1223 and 1447. And then events D and E are so old and poorly constrained that they're, for the most part, not going to be, well, not for the most part, we're not going to talk about them anymore after this. They're very old, coming from old units. So I'm just going to get rid of them. And then add our data to the current view and to the current model of the San Andreas Fault. So here we see our event C. Some clear evidence that this is an out-of-sequence earthquake, being that Bedart-Fan records 3 events in between that evidence and our penultimate. But we also have a much tighter constraint on when this penultimate event occurred compared to what they have at Bedart. But as with dating and using radiocarbon, essentially in OSL, you will have uncertainties. So I just kind of want to talk about one of those cases. Oh, I did these. One of these cases, which is particularly important, is the case of sample T32. T32 is a particularly important radiocarbon sample that we had because it post-dates our penultimate earthquake. Here we have event B, and there is the unit that we found T32 in. But it is a lone charcoal sample, and if you date it individually in OxCal, you actually get 2 equally probable ages for it, one in the early 1600s and one in the late 1700s. So the OxCal model prefers the late 1700s. And a big reason for this is that we were able to confine it or constrain it using OSL samples. And the OSL samples gave confidence to that later age, at least as far as OxCal is concerned. But it's a good solid date. It's a good age to work with. But I wanted to see if we could add data from other sites to try and help expand the picture and make the ages more thoroughly constrained. So that's when we get into the discussion. So now we're going to start adding ages from other sites. Just a quick recap on the context, because I just spent a lot of time talking about earthquakes and charcoals and OxCal models. But I just want us to remember what we're looking at and what we're dealing with here. We have Fraser Mountain, Van Matre Ranch, and Bedart-Fan. They're all in here. This is kind of the particular area that we're going to be looking at going forward. The proximity of Van Matre Ranch to Bedart-Fan, again, made us believe that hopefully we'd get a very similar record. We didn't get that in terms of earthquakes, but if we're going to be combining data from the sites, specifically age data, the proximity makes that a more confident assessment. We will talk a little bit about Fraser Mountain in a sec, but let's go ahead and add some data from Bedart-Fan and kind of see what the difference is. Now these are OxCal models that we constructed, that I constructed. And so we add the Bedart ages and we see a couple of differences. The first big one is that, like I've said a couple of times now, our event C is out of sequence. So So we're essentially now making our event C the same as Bedart's, at least in this particular model. We also get a tighter constraint on our penultimate earthquake. We eliminate about 20 years of uncertainty and have about a 95 to 96 year window where our penultimate earthquake might have been occurring. So with that, we have two cases going forward with these two models. Case one is a large penultimate earthquake. Using our new age data here, and assuming that this is one single rupture from Bedart fan through Fraser, we call this the case one large penultimate event. The other possibility is that they're unconnected. Those are pretty much the two possibilities. They either are or are not connected. This is a question that can't necessarily be answered. Well, it can't be answered by my study. Either are somewhat equally probable. I do have a favored hypothesis, but this is something that could be tested by a complementary paleoseismic site closer to Fraser Mountain to see if you get evidence for an earthquake there. But as a working hypothesis, I believe it's more likely that case one is in fact what was occurring. And the reason for this is that if you look at the record so far, every single Bedart fan rupture has a corresponding rupture evidence from Fraser Mountain. Again, remember that the only reason we're not seeing this sixth earthquake from Fraser Mountain is because they weren't able to constrain it well. But they did have evidence, and it was in between these two ruptures. So you have every rupture from Bedart fan making it as far south as Fraser Mountain. There's only one evidence where you have a Fraser Mountain earthquake that doesn't seem to make it to Bedart. So rather than being unlike most previous earthquakes in the last 1,000 years, I think as a working hypothesis, it's more interesting to deal with a single large penultimate event. So going forward, we're going to talk about the implications of that and what we can do with the data assuming that. But just remember that this is something that needs to be tested still, and that essentially the local penultimate event would mean that we have a better constraint on the penultimate in Bedart, but there's not really much else to say. So it's more interesting to talk about case one anyway. Have a single, actually let's go back for just a sec. So now we can assume, if we're using case one, we have 1857, a single rupture for the penultimate earthquake from Bedart through Fraser, and then we're going to maintain what's already been essentially hypothesized, which is that this rupture, event C, is also continuous. So using that, we will add the Fraser Mountain ages, which, as you can imagine, creates a much tighter constraint on our penultimate earthquake. Now we've narrowed it down to a window of approximately 60 years. And then finally, we put them all together. So earthquake ages based on all three sites, VMR, Bedart, and Fraser. We get a, again, tightly constrained penultimate earthquake, about 60-year window, and then event C between 1563 and 1626. Now, what we can do with this is a couple of things. We can play with the data. Assuming elastic rebound, which is essentially that if you're accumulating slip, that slip will be released during the earthquake, we can do some basic calculations. The calculation would be that if you have 100 years in between two earthquakes with a slip rate of 34 millimeters per year, 34 millimeters times 100, you should be accumulating 3.4 meters of slip, right? So using that simple calculation, we can calculate for the expected slip of the penultimate earthquake and for 1857. This is given here, where we calculate the mean age of the penultimate earthquake and the uncertainties and come up with a number of 5.4 plus or minus 2.1 meters of slip expected during the penultimate earthquake, if we assume elastic rebound. So these numbers are important because there are studies done on the actual slip for each of these earthquakes as measured. There's a number of them. But the most recent studies find that for 1857, we're getting 5 to 5.5 meters of slip and a hypothesized similar level of slip, something like uniform slip, going back for the penultimate and for the third event. But we have measurements going all the way up to 10 meters and 7.5 meters for 1857 and the penultimate. So let's take a look at that. These are our actual numbers Like I said, we have the 5.4 plus or minus 2 for our penultimate. And then we have an early, middle, and late calculation given this age constraint, 1724 being the early, 1784 being the late, and expected measured slip. Now, I'm not trying to say that, well, this is how much slip occurred for the penultimate earthquake. But this is the type of data that you can take and test. You can do stream channel measurements. You can try and confirm this kind of data, and you have a working hypothesis to go with as opposed to just measuring the streams at random. For example, this 4.5 being the most potential displacement with using elastic rebound for 1857 doesn't quite match up, although it's fairly close to that 5 to 5.5 meters of slip. So that's an interesting thing to look at and to deal with. Is there anything else I want to say about this? No, I think that's pretty good. So to conclude everything, taking it back to the solid data that this site was able to give us using only ages from VMR, we have our earthquakes constrained to these very specific ages, with events C, D, and E being out of sequence. As I said, I believe the most productive current model for the penultimate earthquake is a single rupture from Fraser to Bedart, which in that case would constrain the earthquake age to this period, 1724 to 1784, and that using elastic slip, you can expect, or should expect, these kind of measurements of displacement for those earthquakes. These measurements are testable, like I said, via slip measurements. I know there's going to be a study this upcoming summer on stream channel displacements at Van Matre Ranch, I believe. So that's a chance to test some of these. Another thing to note is that the recurrence interval for the most recent 3 earthquakes is a great deal longer than for the next 3 earthquakes. If you're talking about the last 800 years, we go back a little ways, there's a greater frequency for these earthquakes than there are for these earthquakes, which is an interesting dynamic when you consider that we also haven't seen anything from the San Andreas Fault on a big scale since 1857. And that's it. Those are my works cited. Thank you. If you have any questions,